Okay, well, good afternoon, everybody. And welcome to this Saturday lunch panel discussion at MACS 2019. My name is Steve Schaeber, and I'm the manager of service training for MACS Worldwide, the Mobile Air Conditioning Society. I'm also for those of you who don't know me, I'm also the tech editor of MACS publications like Action Magazine and the MSR. To begin today's topic, I'm going to start by giving you a little background on the subject material that we're calling today Condenser Replacement and Precautions. So last summer, actually probably May or June of 2018, I started working on a MACS service report about how to charge a mobile air conditioner when you don't know how much the charge is supposed to be. It kind of spun off of last year's Saturday lunch. You know, because we don't really have too many problems with automotive systems, but off-highway, heavy truck and equipment, you know, it's often difficult to find if there's a label on the vehicle, and then if not, how do you find out what the charge is supposed to be? So a lot of times, guys either know, oh yeah, that takes a pound, or this is a pound and a half, or else they have to figure it out on the fly, real time out in the field. So I was going to try to put something together to kind of have a good recommended practice that guys could use in the field. So how do you charge a MACS system when you don't know how much refrigerant it's supposed to have, such as no underhood label, and you can't find the factory charge spec? So I actually heard of a few different methods, and I read a few procedures, but I wanted to ask the experts. So literally, the MACS experts like yourselves, and come up with this recommended practice that we could use in our training classes and for our, you know, to help our members. So I actually thought it would be pretty simple. All I'd have to do is conduct a little survey, you know, kind of get the responses that I got in, aggregate the results, do some tests on my own at MACS and out of a couple of my buddies' shops, and then put something together that would work for most vehicles. Right? But as you can imagine, that's a lot easier said than done. For the most part, the responses that I received were pretty similar, but none were exactly the same. As you know, the particulars of the system you're working on have a lot to do with whether or not your charging procedure is even going to work. So for example, if you have a charging procedure that's designed for an orifice tube system, it's probably not going to work on a system that has 2 evaporators with expansion valves and a variable displacement compressor, which I found out is like the trifecta of the most difficult to charge determination systems. So I started to dig some more, and I actually came across an unresolved issue, which there's like some under rumblings in the industry, whereby shop technicians are inadvertently overcharging systems with refrigerant after they replace an OE 6mm condenser with parallel flow types. In most cases, the technician has no idea that one condenser is any different than the other. We may be able to look at it and see that they're clearly different, but in a lot of cases, guys out in the real world just don't know. And so what they do is they'll do a condenser swap out, look at the sticker and say, well, there's the charge, stick it in, and then next thing you know, they're dealing with high head pressures and cooling issues. But in most cases, the technician has no idea about this, and they don't know that there's a difference in the internal volume of the condenser itself. So when they see these sky-high, high-side pressure gauge readings, they figure either the condenser that they just replaced is defective, or maybe some other part, usually. What do you say? What are you thinking? What's in your mind? The compressor, right? The compressor is the problem. The pressure is too high. So they go and they order replacement parts, or sometimes they place an order from a different part supplier. Again, they think about that the parts are defective, they order replacement parts once again, and this continues until maybe somebody gets the technician in touch with a tech support guy like me or like Richard, who explains to them that they probably overcharged the system and that a charge calculation procedure needs to be done. Although things usually do get worked out in the end, it's the parts store, right? It's the wholesale distributor, the parts distributor that gets stuck with this pile of return defective parts that probably aren't even bad, but they can't resell them as new parts anymore. So as it just so happened, this past summer, one of my fellow MACS staffers who you've probably said hello to in the last couple days. She owns a 2006 Ford Freestyle, the station wagon of SUVs, that still had the original 6mm condenser. So we looked it up. We found the majority of the aftermarket parts available were in fact parallel flow type. Although the 6mm is still available, but it's at a much higher cost. So I thought, hey, this may be the perfect project car to work on, a good candidate for me to use for a charge determination procedure. And I called up Ranchu and asked them to support the project with a condenser donation, which they did. So, me just sitting thinking about this on my own, I want to try to improve my results, my chances of success. So I asked MACS MACS trainer and recent board of directors nominee Tim Iezzi to give me a hand. So I drove out to his shop in Reading, Pennsylvania. We started out by baselining the Freestyle with an accurate charge, measuring the pressures and temperatures, and then we recovered and swapped out the condenser. But since this one is presumably smaller internally, we expected that the charge level needed to be reduced to compensate for that smaller condenser size. The procedure that we followed had us start out with a 1-pound refrigerant charge and then adding more refrigerant in 2-ounce increments, while at the same time we're keeping an eye on pressures and temperatures and calculating condenser subcooling so that we can determine how much liquid was in the condenser. But I told you about this trifecta, right? The whole time we're doing this, that variable compressor is working against us, compensating for the variable charge amount. And in the end, and after a long day of testing, it was actually easier for Tim to just use his years of experience and charge the system by feeling the suction line for that slug of cold refrigerant to come through. And then watching for superheat to drop at the evaporator outlet, rather than following a more scientific procedure. But the good thing is that, especially in some pretty large parts of our industry, not all vehicles work in this same way. Some charges are easier to figure out than others. So basically what I've done is I put together this panel of experts today to help us address these issues and see what we can come up with, even if it's just more awareness in the industry for shop owners and technicians. But before I do, I want to ask everyone to please hold your questions until the end, after everyone gets a chance to speak. So I'll introduce our panelists. First is Wayne Herndon, who's the founder of Four Seasons and former president of IMACA, the International Mobile Air Conditioning Association, who currently owns and operates Cool Air Automotive of North Richland Hills in Texas. Richard Hawkins is technical administrator at 1-800-Radiator and AC of Benicia, California. Sherwood Wheeler is a supervisor of dealer tech support for AGCO in Hesston, Kansas, and has been a presenter for many years in the MACS heavy-duty technical sessions. And the man I already introduced a little bit, Tim Iezzi, is a shop owner and lead technician at Iezzi's Auto Service in Reading, PA, who teaches classes for MACS and CarQuest Technical Institute. I'll start out with Sherwood. As the systems in your agricultural equipment are somewhat different than those found in automotive and light trucks, when a technician calls you and needs to know how to properly charge a system when no exact amount can be given, what do you do? What's the procedure that you advise technicians to use? Considering that you generally don't have ram air and variable compressors, and the circumstances under which a technician would use that procedure.
Yes, this is a question we've had come up in the past as well from our technicians that may have attended our training classes in Hesston, Kansas. Normally the question is, I'm out at the farm, I'm out at the job site, I'm there to work on maybe the hydraulics or an engine complaint, and then the customer says, oh, by the way, the AC isn't working or cooling so well on this other vehicle, or this tractor or combine, whatever it might be. They say, usually, how do we know how much gas to put in? I mean, if we hook up our gauges, maybe, they're looking at pressures. And so at that point, we want to go through, or I go through on how to at least determine if we have an adequate charge using condenser subcooling. just a little bit about the systems we use. Typically on ag equipment, we typically use a fixed displacement compressor. We do have some smaller compact tractors that will run a scroll, but for the majority of it is a fixed displacement compressor. As far as the condenser designs, we still use the round tubing fins. We still use multi-flow, or we'll use the parallel flow, serpentine. So we have a whole range of condensers that we use, some with external dryers, some with internal desiccant. And so in addition to that, to going through or explaining how we do a condenser subcooling, at AGCO we also have what we call AGCO University, and back in 2015 I did one of our top tech videos that our leaders can subscribe to for online education or training, and part of that was an advanced temperature testing training video, and part of that I also went through condenser subcooling, so dealers can still log in today, they can review the video, they can go through the demonstration on how to do condenser subcooling. And so typically the working range we're working with is a 10 to 25 degree subcool. That's the window we work with. I've checked the subcooling on a lot of AGCO equipment, whether it's a tractor or windrower or whatever the product is, and typically what I see, our subcooling that the engineers have calculated, they typically work in the 15 to 20 degree subcooling range. Now, what are some of the requirements whenever you're checking subcooling? I'll go through that process, and that is we normally, we've got our engine set 800 to 1,000 RPM. We want to make sure that the cab blower fan is on high speed, max heat load across the evaporator, so doors open, windows open. I want maximum heat load across the evaporator. I also want to make sure that I have good airflow through the condenser. And today, of course, we're working with different designs as to how that engine airflow is controlled, whether it's a fixed radiator or a fixed fan on the engine, whether it's a viscous fan. Fortunately today, we control those electronically, and if we unplug the viscous fan, it defaults to max engine speed or max airflow. And so we want to make sure we have good airflow coming across the condenser as well. And the other key is make sure the hood is closed, because so many times I've run into techs, they'll open the hood, they'll hook everything up, and then you get some readings that do not make any sense, and it's the fact that you just open the hood. And so you're bypassing the condenser at that point. So normally we will wait a minimum of 5 minutes. I'll normally go up to 10 minutes, and then I'll take my high side pressure reading. I'll use a PT chart. I will convert that to a temperature. I will use a contact probe. I'll measure the condenser outlet line. I'll subtract the two numbers, and that gives me my condenser subcooling. And so that's an easy method for us to do. With ag equipment, we don't have a whole, in the past we haven't had a lot of information on refrigerant charges. I know I've provided on the shift mobility on the MACS site, we've provided all the refrigerant charge recommendations that we have going back to the R12 days. And even then, some of the charts or models you've seen, they don't even have a refrigerant charge, because in the manual all it said was charge until the bubbles go away. And so that was a charge. And so this is where condenser subcooling comes into play in those older units. If you're below 10, we would consider that an undercharged system. If we're above 25, then that's where we would start looking at, okay, is the system overcharged at that point? That would be the suspect. Again, the important thing is the key is airflow. Airflow across the evaporator, good airflow across the condenser, max heat load on the evaporator, and then go through the process. If it's undercharged, then we would add 1/2 ounce to 1 ounce. We would then wait 5 minutes. We would do take the high side pressure reading, again convert it to a temperature, take my condenser outlet temperature, and then minus the two numbers to see what my condenser subcooling is. And if it was still low, I would continue to repeat that process. We don't get into a lot of changes in our condenser designs, you know, whether it's the original condenser. We find most do come back to the OEM. We do know that there are some aftermarket condensers that are, you know, are being sold through other outlets, and I think from what I've seen so far, most of them are sticking with the OEM design.
Thanks, Sherwood. So, Richard, you handle tech support directly for customers of your company's franchise locations. How does the scenario that I described with the Freestyle affect these technicians, the shop owner, in your case the franchise owner who has to deal with these return parts, and the company as a whole? And kind of at the same time, like how big is this, how big of a problem is this for our industry? And of course, what are your recommendations for technicians to do when a situation like this comes up and they're on their second compressor install and they still can't figure it out? What do you tell them to do?
Wow, you covered quite a bit there.
Yeah, not that much.
There can be a lot of frustration that results because of this. Typically when I get involved is when somebody has been struggling with a system, maybe for a few days, just can't get it to cool properly. The head pressures are too high, and it's because the condenser has been changed, design has been changed from what the OE unit was, and they don't know that that's the case. We've taken steps with our catalog and to address this issue where we have our condensers listed and we show what the original style is, and if it happens to be a 6mm, which is also known as a piccolo condenser, we'll have that listed there, and we'll have a notation in there: improved design, newer design may require reduction in refrigerant charge. And in a perfect world, whoever's selling that condenser will relay that information to the shop that's buying it, and whoever is taking delivery of it in that shop will take, or on the phone call, will convey that information to the technician that's working on it. Well, a lot of times, all that information doesn't get transferred, and the technician doesn't know what's going on there. And with a few rare exceptions, most condenser manufacturers don't put anything in the box or on the unit to indicate that the design has changed and the reduction is necessary. So you get into a situation of where they might have replaced multiple parts on the vehicle, they still can't get it to cool, and I get a ticket that comes across asking to call someone and talk to them, and the first thing that I was going to ask them is, okay, you got the vehicle close by that you're working on? Yeah, I've got it out in the bay. Can you go out and take a look at it? Tell me if it is if the condenser has flat tubes or if it has round tubes. So they say, you know, they say, well, what do you mean round or flat tubes? I'm like, the horizontal tubes that run across from side to side that the refrigerant flows through. So they'll go out and they'll take a look at it and they'll say it has flat tubes. So, you know, I'll go a step further and I'll say, okay, do you happen to have the original condenser sitting around anywhere? Well, yeah, I've got it sitting over in the corner. Well, walk over and take a look at it. Now, if you look at that one, it probably has round tubes, unless it's been replaced somewhere along the line, and it has 180-degree bends on one end. Yes, that's the way it's constructed. I said, well, the issue that you're dealing with there is you have a parallel flow condenser in this vehicle now. It originally came with a 6mm condenser, and it's necessary to reduce the charge. So the next question is, well, how much do I reduce it? And unfortunately, there's no concrete, precise answer to that. It involves temperature testing, temperature charging to establish a charge. Some of the stuff that my counterpart here alluded to. Well, most shops are not aware of any of that, and worse, they don't have the necessary temperature testing tools to be able to do it if they did have the knowledge and all on it. So they get extremely frustrated, and sometimes, unfortunately, what they end up doing is just reducing the charge, just kind of taking pot shots at it, hoping that they're going to hit it, and sometimes they can go ahead and get it to cool well, but the problem is on an orifice tube system, which is where we run into most of this, an orifice tube system can cool great with a 25% undercharge. But what you don't see is that the compressor case temperature is elevated dramatically, and after the compressor runs for a while, the amount of oil in the compressor is reduced dramatically, so you get a double whammy going on. You've got a minute amount of oil in the compressor, and it's operating at a much higher temperature than normal, so then they end up with a compressor failure. So it's something that can be extremely frustrating. And our recommendation to them is, if you can get another 6mm condenser, then replace it with a 6mm condenser. Don't replace it with a parallel flow. That way you don't get into all the stuff. Another thing that you get into, if one is replaced with a parallel flow, and they do the proper temperature charge, and if they forget to put the change amount on the decal on the vehicle somewhere in the future when somebody works on it, they're not going to be aware the condenser was changed. They're going to put the factory charge back in it, and they're going to have head pressures that run through the roof. So our recommendation, if at all possible, replace it with a 6 millimeter. But there are some instances where you can't get 6 millimeter condensers anymore for some of these vehicles, and you have to go with the parallel flow. And when you run into that situation, then you've got to alter the charge based on information such as he covered there. So that's a situation that exists.
Thanks, Richard. So Tim, you and I spent quite a bit of time working on this. You actually helped me do the work on that freestyle. Can you describe the procedures that we used and why it was easier than following the many instructions that I had gathered together? And since we talked about this a lot before we actually did the work, I know you thought about this for a long time. Did things work out the way you expected given the car we were working on?
So basically what we tried to do, as Steve said, we started with a pound of refrigerant in the system. I believe the label charge was somewhere around a pound 11 ounces maybe, something close to that. And what we figured we would do, we set up using temperature measurement devices, contact thermocouples, measuring our temperature in and out of the condenser and measuring your temperature out of the evaporator core. Unfortunately, because of the design of the vehicle, it would have been ideal to be able to measure the temperature on the evaporator inlet on the evaporator side of the expansion valve, but because where the expansion valve was placed relative to the firewall, there was no way that we could do it. We spent about an hour trying to. There was just no way that we could get a thermocouple in there to do it. What we wanted to do after we put the condenser in, and we put the correct amount of oil that Ford said needed to go in this compressor, evacuated the system, put our pound of refrigerant in, ran the vehicle. We tried to create max heat load on the vehicle. We had electric cooling fan running. This vehicle had a pulse width modulated variable speed cooling fan. So PCM was in control of what our fan speed was. We wanted to add 2 ounces at a time, recording what our condenser and inlet and outlet temperatures were, what our suction line temperature was, looking for the amount of superheat that we had out of the evaporator, trying to bring the superheat down close to what the superheat setting on the expansion valve was, and looking what our condenser subcooling was. We expected, based on the physical size differences between the condensers, that we were going to need somewhere between a 4 and 6 ounce reduction in charge, just looking at the physical size differences. So we started charging it. After we'd add 2 ounces to the system, we would let everything stabilize. And what was interesting, as we're adding refrigerant, our temperature numbers really weren't changing. We still had about the same temperature drop across the condenser and this very similar suction line temperature. Eventually we got all the way up to the label charge, and just as we were coming up to the label charge, our suction line temperature started dropping. We started seeing a reduction in superheat out of the evaporator core, indicating that we were getting close to where our charge was. In the end, I wound up shipping this car actually 2 ounces over what the label charge was where we started. We had a cold suction line, like Steve alluded to. I was feeling for when the suction line temperature started dropping, indicating that I had an evaporator just about full of liquid and able to cool, which was very surprising. We never expected that we were going to have a more higher than label charge into this vehicle. Really not sure. We never did figure out why, but that's kind of where we wound up with it. And even through all of that, between 1 pound and a pound 13 ounces, our temperature difference across the condenser never really changed. I kind of suspect that was in part due to the variable speed cooling fan. As pressure would start coming up, our fan speed would increase, and then our pressures would come back down, our temperatures would go back to where they should have been.
Right. So Wayne, you came across, you actually have been working on this for quite a while. The trifold brochures that we handed out, you wrote those. So it's been a number of years. And you've actually written a whole training program topic about this. And you also teach it too. You've done a lot of case studies, swapped out condensers yourself on several cars in your own pickup truck, multiple condenser swaps, trying to determine the correct refrigerant amount based on these different condenser sizes. So what charging procedure do you recommend?
Okay, thanks, Dave. I've got to say a couple of things up front. In my 54 years in this business, I had the privilege of starting this business working behind a 50-ton fin press, pumping out aluminum fins, sticking copper hairpins in there, and raising up tube and fin condensers. The engineers that I worked with at a company, foregone company called ARA, kind of gave me an education. I can remember one of the things they quoted to me is early on in my career, I still remember some of these things, condenser is the heart of the heat exchange in the system. At that time, the expectation was, this was 1965, that you would see about a 30-degree change across the condenser. From that, through my history in this business, 40 years of that time, I have either worked for a company building air conditioning systems, aftermarket units, or own companies that we install thousands of aftermarket units. And my attention has always been the condenser, optimize the size, make sure it's close to the radiator, getting it to position of proper airflow. So I come from this direction a little bit different than some others, and I'm an absolute believer in my training classes of temperature testing. The brochure that you see there is this one of the second studies that we did, my friend Peter Picardo from Four Seasons over here. In this particular case, we started with the 1995 or years with the 96 Ford F-150 accumulator system, and we started with 3 brand new condensers just to kind of set the stage for what the change was. I normally have a slide to show this, but I find it's easier when I deal with technicians at a training class, and I'm dealing with people that are buying condensers, buying a kit, maybe with a condenser in it, and showing them how to get the proper charge in it in the most expedient way, and then normally, and how we did it. So to start with, you'll see we have, in this particular case, we have the yellow as a factory condenser, which is a factory Piccolo, Motorcraft new condenser. We have the green is the serpentine condenser, which is a flat tube that runs serpentine back and forth that has a number of tubes inside of it. And then we have the micro tube, my terminology, the micro tube parallel flow condensers. Parallel flow condensers, and as Steve has asked, what's one method? As you went to the show yesterday and walked around, you see a lot of different condensers. I picked up, I think, 4 different cutouts. The cutout that I have brought tonight is one of our older cutouts, and if you look at those, and even with trifocals, it's a hard time to do it, but there's approximately 14 holes in each of those tubes in that parallel flow block you have. At the show yesterday, you could find condensers that were parallel that would go from maybe 14 to as much as 22 holes in that same width of a condenser. So even within parallel flow to parallel flow, it's different. So we try to find a logical way to approach this. And in this particular case, this Ford pickup, which was the accumulator system that we're dealing with, had a 33-ounce charge, as you'll see on the far right of the graph we show there. And as Richard said, what we have here, we have several data points. We put the brand new condenser in. This took us 2 days to do it. We actually heated my shop up in Fort Worth, Texas to about 80 degrees consistently and made it be as thorough as we could. So when we started at 21 ounces of refrigerant is where we started, 19 ounces on this chart is where we started our charge, knowing this was a 33-ounce factory charge. You'll see as you go from 19 ounces, you'll go down, you'll see how the condenser temperature changed. Very radical temperature changes, 78, 72, and 68. You'll see where I am at with the different condensers. And then we have the evaporator temperature change. I'm an advocate of temperature change, so whenever we're doing, my process, I should say, that we used in this, is because it's a flooded system, the first thing I needed to do, or I recommend that the technician do, is make sure that evaporator gets a flooded level, meaning the same temperature in and within 2 degrees with temperature coming out. So as we go across, that's the first criteria, because if you're low on the coolant level, or refrigerant level in the evaporator, as Richard just mentioned, your case temperature of the compressor will get too high and you'll have a compressor failure. So the third data PID that I have at the bottom actually shows you what the compressor case temperature was as we incremented this, going across this charge. My philosophy is with a 32-ounce system or 33-ounce here, add 2 ounces at a time. If we're working on a 17, 18-ounce system, 1 ounce at a time, and then give it time to stabilize as you see it goes over. I won't take a whole lot of time to read you numbers, but you go from 19 to 21, and at 23 ounces, you'll see the blue all lines up from top to bottom. I call this the sweet spot. This is the micro 2 parallel flow condenser, and you'll see at this particular point, we've hit 40-degree change across the condenser. That's a target that we've used now for about 10 or 12 years. With micro 2, with the subcooling parallel flow condensers, have the dryers attached, we're seeing some 48s and some 52s and 54s. But for this purpose, 40 is where we tend to zero in on what we're looking at. So at 40 degrees, you'll see that's about the same time I also hit 0 in the middle column. That means I have the same temperature in and out. I do not have at 21 ounces, I was 22-degree difference between the inlet and the outlet of the evaporator. So we knew the evaporator would be low on liquid. You would be starving for lubricant going back to the compressor. So that's one of the bogeys that we wanted. And you'll see our compressor case temperature from the first column to where we're at went from 162 degrees to 128 degrees. And I apologize for my trifocus here. So that was a sweet spot. That was the ideal temperature we found with this micro tube on this 1995 Ford pickup. Now, it's going to change a little bit from car to car, but this is a study that basically gave us an incremental way to measure data PIDs as it goes across. The other thing I will say about condensers, when I first learned about condensers back, when I was still, we had horse and buggies out there, was the expectation of what a condenser did. You basically start with a high pressure gas, and temperature of that gas had to exceed your ambient temperature, coming across the grill. And the rule of thumb back there, or at that time I was told, was about 50 degrees. I will point out that even though we don't have the data PIDs here, while we were doing this, we also saw some reductions in head pressure. By reducing head pressure, you're reducing the temperature. As the more efficiency, the higher efficiency condenser you have, the lower your head pressure is going to be because you don't have to get a 50-degree climb from the temperature of the refrigerant to the temperature of the air going through the condenser. I dare say these newer condensers, micro tubes, maybe a 30-degree differential between inlet temperature of the refrigerant to the air temperature going across the condenser gives you, a sufficient transfer from high pressure gas to high pressure liquid. So there were other achievements that we picked up here that would show potential fuel economy, things like that. Now, that's 23 inches, that's 23 ounces. That's 10 ounces less than what the factory charge was. To prove what's happening, as we've described, everybody's described with an overcharge, we continued in every case to go all the way to the 33 ounces. So you'll see we went from 23 to 25 with no real benefit, as far as the other condensers. We went to 27. I would point out that in this particular case, at that blue line that we hit at 23, we went from a 40-degree change across the condenser. Now at 27 ounces, I'm down to a 32-degree. I've lost 10 degrees efficiency of the condenser. The green bars that you see lined up, that's a serpentine condenser. This is a serpentine condenser. It is preferable to a piccolo. Also, some of the manufacturers still offer these out in the marketplace. So at 27 ounces, we hit the sweet spot, with the serpentine condenser. 40-degree change across the condenser, the evaporator is flooded, and 125-degree or 128-degree compressor case temperature of the compressor. Now we're still 4 ounces below the factory charge. We keep moving over to the 33-ounce charge. This is the factory charge. At 33 ounces, we have a 42-degree change across the condenser, a 2-degree change across the evaporator, still within tolerance, and 135-degree case temperature. The point that we make with this, that we achieve with this, is the way we recommend charging is undercharge, a substantial amount if it's a piccolo to parallel flow. Within the parallel flow family, however, just as Iezzi said a minute ago, you can get a parallel flow to parallel flow, and as I said, 14 holes in the condenser to some of them with 16. You have to even overcharge some, maybe an ounce or two. But to undercharge it a little bit and use an incremental charge to it with particular data page that you're looking at will give you a rapid way to get a sweet spot, as I call it, just determine what the charge would be on that one vehicle. I understand what Steve said as far as making a note of what you put on there, what the final charge would be. You know, that's also advisable. But the thing I also try to emphasize with students, that depending on the brand and, you know, manufacturer of the condenser, you know, this can vary quite a bit. I emphasized a couple other things quickly. This is a parallel flow condenser on a accumulator system, orifice tube accumulator system. When we do this, you know, with a TXV system, we do the same thing. We're monitoring the temperature coming out of the firewall.